Hello, and welcome to the Assessment of Existing and Potential Volume Reduction for Post-Construction Stormwater Management webinar. My name is Paula Hyman from the Ohio LTAP Center, and I'll be your technical support for today's webinar. Before we begin, just a couple of housekeeping items. If you have questions throughout this presentation, I ask that you please type them into the questions box. Our presenters will address your questions at the end of today's presentation. And this presentation is being recorded. Providing that the recording is successful, a YouTube link and a copy of the presentation will be emailed to all participants and uploaded to our LTAP website. I'd like to thank you in advance for your participation, and I'll pass things off to Mr. Justin Kearns, Water Resources Engineer with MS Consultants. Justin?
Thank you. Thank you again, everyone, for tuning into our presentation. Presenting with me today will be Greg Colton from the United States Geological Survey. And without further ado, we will go ahead and jump into our presentation on soil amendment for stormwater volume reduction. I'm going to turn my camera off just to help with the network speeds here. All right. So to begin, we'll do a quick introduction of our research team. MS Consultants served as the principal in charge and the principal investigator. We are responsible for composing the reports, as well as conducting hydrologic analysis and producing construction plans. The United States Geological Survey, USGS, was in charge of flow monitoring and hydrologic analysis, and they served as the co-principal investigator on the research project. Stone Environmental was responsible for putting together the soil amendment plans and assisted with the report preparation. Buds Inc. served as the general contractor and also provided consultation for construction and soil amendment construction. The research objectives. The problem was that ODOT wants to avoid having to purchase additional right-of-way for large post-construction stormwater detention BMPs. It's expensive and it increases the project footprint. The Ohio EPA and ODOT both allow underground detention and manufactured systems, but they're not preferred. Underground systems are expensive to construct, and they're often expensive and difficult to maintain. So ODOT wanted to develop an additional option for managing post-construction stormwater quantity on ODOT projects. The goal is to provide a low-impact, cost-effective alternative stormwater BMP that could be sited in the ample available green space along ODOT roadways. This is currently underutilized space. The concept for the new BMP is soil amendment. By amending the top few inches of native soil with higher infiltrating and nutrient-rich materials, we can increase initial abstraction, infiltration, and evapotranspiration, thereby reducing runoff from the roadways before they enter storm sewers, creeks, and rivers. The prospective BMP would also benefit ODOT in terms of offsite mitigation potential. As demonstrated by the image on the right side of the screen, narrow, impervious roadway corridors don't provide a lot of opportunity for stormwater management, except for underground detention or manufactured systems, which are hard to treat. These areas are hard to treat. However, the areas, as you can see in this image on the north side of this picture, have a nice wide grassed median that can provide more cost-effective stormwater treatment. That is what this prospective BMP aims to take advantage of. This project was kicked off in May of 2017, which, as hard as it is to believe, was over 4.5 years ago. We conducted 1 year of existing conditions flow monitoring, which ran from March of 2018 to March of 2019. Monitoring was suspended during winter months because of snow and ice may interfere with our runoff data and skew our results. I'll cover more details on the flow monitoring setup and the equipment in the next few slides, but essentially we wanted to establish a baseline and determine how much runoff is occurring along typical ODOT roadways currently. Then we installed various amended soils, which again I'll cover in more detail in the next few slides. After the amendments were installed, we conducted over 1.5 years of post-amendment flow monitoring to see what impact the soil amendment had on runoff quantity. The runoff data analysis will be covered in detail by Greg a little later on. And now we're in December 2021, and we are wrapping up our final reports and recommendations to ODOT. The research team found sites across the state of Ohio that were ideal for flow monitoring. The criteria consisted of grass shoulders and side slopes within ODOT right-of-way. We looked for areas that were generally consistent with the current vegetated filter strip BMP, that is, wide, grassed, shallow slopes that receive sheet flow from the roadway. We found that medians provided the best location due to the controlled drainage area. There are no contributing drainage area from outside the ODOT right-of-way, and a high percentage of the flow was from the paved roadway. We chose wide medians that provided ample safety for installation and maintenance crews. We also looked for areas with guardrails to protect equipment and crews when possible. Distributing the sites across the state allowed us to capture a variety of rainfall patterns. This map shows the 12 monitoring sites that we selected. There were 4 along State Route 161 and State Route 16 between Columbus and Coshocton, and another 8 sites along US 30 from Bucyrus to Canton. 2 of these sites were control sites, which did not have any soil amendments performed. The control sites were co-located next to another site that was amended. As you can see in this image, we've used a color coding system. The green and yellow boxes there to show which sites were co-located with control sites. That color scheme will be mentioned later on by Greg. BMP 2 and control site 1 were co-located, and BMP 7 and control site 2 were co-located. This allowed for a direct comparison of runoff between an amended site and a non-amended site. The control sites also helped identify any major environmental or rainfall changes between the 2 monitoring periods and helped isolate runoff variables during data analysis. Again, Greg will cover this in more detail shortly. This picture shows the monitoring equipment setup installed at each monitoring location. Rainfall was captured using a tipping bucket rain gauge, and flow data was captured through H-flumes, which were installed in the ditch line just upstream of an existing catch basin to capture all flow coming off the roadway. Wing walls prevented flow from bypassing the equipment, and during periods of runoff data, photos and data were collected at 1-minute intervals and transmitted to USGS via cellular data, all this powered by solar panels. The research team evaluated numerous natural and manufactured soil amendment materials with the intended goal of improving the soil porosity, texture, and capacity to hold moisture in order to improve the soil's long-term capacity for infiltration and exfiltration. The team decided that sand, expanded shale, and compost would be the best materials to install for field testing. For those who don't know, expanded shale is formed when shale is crushed and fired in a kiln. This process causes tiny air spaces and air pockets in the shale to expand, making a semi-porous aggregate. The idea was that the sand or expanded shale could provide the infiltration and moisture capturing benefits, while the compost would provide vital nutrients and organic content to maintain robust vegetation, which will also aid in runoff reduction. These images show the general construction procedure of the soil amendments that we used out in the field. We ripped the soil initially to loosen it up, then removed the top few inches to make room for the added amendment materials. We placed our amendment materials and then rototilled it in order to incorporate the material into the native soil into a single homogeneous soil layer. We then applied a compost blanket, seed, and erosion control mat in order to reestablish vegetation. We then we decided to leave the bottom of the median swale undisturbed. This is because we wanted to measure the effects of the soil amendment on the sheet flow across the side slopes, and not necessarily the soil amendment's impact on concentrated flow in the ditch line itself. These pictures show the monitoring sites immediately after the soil amendments were constructed. The image on the left is in March 2019, immediately following construction, and then a few months later in June 2019, after the vegetation had a chance to reestablish. Now I'll turn things over to Greg Colton to discuss how we analyze and compare the pre and post BMP flow data.
Thanks, Justin. So we ended up computing data for what we called events. And an event begins when the first 1/100th of an inch of rainfall is recorded. And it ends when the measurable rainfall and runoff both have ended for at least 3 hours. The events were divided into 2 periods. One we called a pre-BMP period, which was before the soil amendments were installed. And the other was the post-BMP period, which is the period after soil amendments were installed. Let's see. Okay, so this is an example of one of the events. And in this case, it illustrates an event that had runoff. The blue line shows the runoff hydrograph and the red line shows the cumulative rainfall. And you can see here that the rain begins, that's when the event begins. And then runoff actually begins later after the rainfall has begun and peaks up here. And then eventually the runoff ends, but the runoff ends after the rainfall has ceased. And so from the point at which the runoff ended, we wait another 3 hours to end the event. And so we end up having an event duration that goes from that beginning of when the rain started to 3 hours after the runoff ends. Oops, sorry. Another example of an event, and this is for one that that didn't have runoff. And in here you can see in that cumulative rainfall graph that there's rainfall and the rainfall ends, but that blue line that shows the cumulative runoff shows that the runoff remains 0 the entire time. And so again, the event began at the beginning of rainfall and ended 3 hours, in this case, after the rainfall ended because there was no runoff. So the rainfall totals were used to compute the volume of rain falling over the catchment. And the volume of runoff was measured with the calibrated H flumes. And it was divided by the rainfall volume, and that ratio is sometimes referred to as the runoff ratio, and then multiplied by 100 to convert it into what we call a runoff percentage. So we computed information on event duration, event runoff, and event rainfall totals and intensities, and also runoff percentage for more than 4,200 events. And so it was an average of about 350 events per site. So there are several questions we tried to answer. The first was, did event percentages change from the pre-BMP to the post-BMP period? So this table shows total rainfall and runoff volumes and runoff percentages computed for each site for the pre and post BMP periods. The red highlighting indicates where runoff percentages decreased in the post BMP period. And we noted several things. First, that the total runoff percentages varied appreciably between sites, even in the pre-BMP period. We also noticed that total runoff percentages did not decrease in the post-BMP period at all sand or shale amended sites. So there was not consistency within a given amendment type. And then we noticed that 3 of the 4 BMP sites with the largest decreases in total runoff percentage had sand amendments. So we also examined information about rainfall distributions. And this is a box plot that shows the rainfall distributions on a site-by-site basis for both the pre and the post BMP periods. And for people that aren't familiar with box plots, I just want to point out that the box extends from the 25th to the 75th percentile and includes 50% of the observations. And the number of observations that is used in constructing the boxes are shown at the top of each one. I'll also point out that normally there's a median line that you can see that's in the center of the box or somewhere within the box. But in this case, because only about 1/3 of the events had runoff, that median line actually falls at the 0 point. And so we prepared these box plots to show the distributions, and sites with sand amendments here have the red filled boxes, and sites with shale amendments have the gray filled boxes. We noticed there were appreciable changes in the span and upper limit of the interquartile range. That's the distance between the 25th and the 75th percentile. So the interquartile range of runoff percentage between the pre and post BMP periods at some sites, like BMP02. However, the changes in the distributional characteristics were not consistent for a given amendment type. So you can notice, for example, this is a sand site where the box seems to shrink from the pre to the post period, whereas another sand site over here, it actually went in the opposite direction. Also, some sites like BMP06 and BMP08 tended to have relatively low runoff percentages even before the soil amendments were installed. So next one. So this plot shows the distribution of runoff percentages, including only those events that had runoff. And this is just being shown to make it easier to see the distributions of runoff percentages for runoff producing events. And in this case, since we've removed those events that don't produce runoff, you can see the median lines in the center of the boxes. But the overall information that's provided on either of them is essentially the same. For example, we noticed, the boxes seem to shift down for BMP02, but they shift up for BMP10. So we wanted to ask the question, were there changes in rainfall characteristics from the pre-BMP period to the post-BMP period that might explain the observed changes in runoff percentages? So again, we looked at the distributions of various rainfall characteristics, and in this case, we're looking at the distribution of rainfall totals. And we were just looking to see if there was an appreciable change between the pre and the post BMP periods. And what we noticed was that the distributions of the rainfall characteristics look pretty similar, both for the pre and post BMP periods. Another question we asked was, were there changes in rainfall and runoff from the pre-BMP to the post-BMP periods that were statistically significant? And so that was accomplished by examining the empirical distribution, empirical cumulative distribution functions, or CDFs, of the runoff percentages and the rainfall. So this plot shows pre and post-BMP empirical CDFs of runoff percentages. That is, the runoff percentages plotted as a function of the proportion of observations less than the indicated value. This particular plot is for site BMP03 that received a sand amendment. And I just want to point out that the red line here is the CDF for the pre-BMP period, and the blue line is for the post-BMP period. So the plot shows, for example, that about 75% of the pre-BMP events had runoff percentages less than 20%. That's what's shown here. However, the percentage increased to about 92% in the post-BMP period. So we're seeing a larger proportion of the observations that have runoff percentages less than 20%. in that post-BMP period. It also shows that the percentage of events that had zero runoff increased from about 58% in the pre-BMP period to about 66% in the post-BMP period. So we were able to use a Kolmogorov-Smirnov test to determine whether differences between the pre and post-BMP empirical CDFs were statistically significant. The Kolmogorov-Smirnov test can detect shifts in the distribution as well as changes in its shape. And only 2 sites, both with sand amendments, had statistically significant differences, irrespective of whether no runoff events were included in the analysis. These was BMP 02 and BMP 03. Most of those sites had sand amendments. There were no statistically significant differences in the empirical CDFs of runoff percentage at the control sites, and there were no differences in event rainfall totals at any of the sites. The final question we addressed was, during the post-BMP period, what factors appear to be associated with the variation in runoff percentage at BMP sites? Sorry. So we used regression analysis to assess the relative importance of the factors associated with the observed variation in runoff percentage at the soil amendment sites during the post-BMP period. What we found was the event rainfall total was the most important factor, followed by a cross product term between event rainfall total and antecedent rainfall. The bottom 7 factors collectively had about as much influence on runoff percentage as the event rainfall total did. And we found that amendment thickness and amendment type were among the least important factors. So, some conclusions we came to were that runoff percentages varied appreciably between sites, even in the pre-BMP period, that neither the addition of sand or shale amendments resulted in consistent reduction in runoff percentages, that 3 of the 4 BMP sites with the largest decreases in total runoff percentage from the pre to post-BMP period had sand amendments, that statistically significant changes between pre and post-BMP periods CDFs of runoff percentages occurred at only 4 sites, 3 of which were sand sites and 1 being a shale site. And then finally, no statistically significant changes were found between the pre and post-BMP period cumulative distribution functions of runoff percentage at the control sites or the event rainfall totals at any of the sites. And Justin, I'll shift back to you.
All right, thank you, Greg. I appreciate the run through and the crunching of all the numbers. You said USGS did a very extensive data analysis, and some of the stuff way above my head, but we appreciate all the work they did with us. So in order to summarize what Greg and USGS did is we took the findings and the conclusions from the monitoring and the data analysis, and we looked at what that ultimately meant for ODOT. What are these results from our research, what to make of all that. And the key takeaways we made was that the pre-BMP runoff percent was generally lower than we expected. And then the post-BMP runoff percent was a little bit lower than that. As Greg said, not consistent up or down, but still, a little bit lower. Sites with a higher BMP runoff percent generally saw a higher reduction than sites with lower pre-BMP runoff percentages. Therefore, sites with the lower pre-BMP runoff percent left little room for reduction. The runoff percent was already low, that there really just wasn't much room to go down from there. They're already generally pretty good from our perspective. We saw a little difference between the sand and the compost amendments. I'm sorry, I should say between the sand and the shale amendments. And we also saw a little difference between the 4-inch versus the 6-inch amendment depth in terms of runoff reduction, runoff percent. Rainfall and environmental conditions don't appear to have caused a significant impact. As Greg said, the rainfall distributions among all the sites remained fairly similar between the pre-BMP and post-BMP monitoring periods. Therefore, based on these conclusions and these key takeaways, MS Consultants has recommended that the amended vegetated filter strip, abbreviated AVFS, BMP be added to the ODOT Location and Design Manual as a water quantity BMP. Amending the existing soils provides soil quality benefits. We saw increased organic content of the existing soil. We saw increased nutrients, increased homogeneity of the top layer of soil. We found the BMP to be space efficient, and it utilizes the grassed medians and the grassed side slopes along the ODOT roadways that are currently being underutilized. And the BMP can be incorporated into existing ODOT right-of-way with limited need to acquire additional property. The amended vegetated filter strip is low maintenance. It doesn't require anything more difficult than what ODOT is currently performing on the existing shoulders and medians. Just some routine mowing and keeping an eye out for rills and other sign of erosion. Like I said before, while we didn't see a large reduction in stormwater runoff volume, what we did see was a slight reduction in a low runoff in general, much lower than expected. The average post-amendment runoff percent was less than 25%. Again, a slight reduction from the pre-amendment period average of 27%. And the maximum runoff percent observed at any monitoring site after the amendments were installed was 37%. Again, down from a post-amendment monitoring period max of 48% runoff percent. So by constructing the soil amendment BMP, we can at the very least increase the likelihood that runoff will be low. The research team conducted cost-benefit analysis and found that the amended soil BMP is a cheaper alternative than the traditional stormwater BMPs currently used on ODOT projects. And I'll explain this in more detail shortly. The amended filter strip is also easy to construct, both for redevelopment projects and for new construction. MS Consultants recommended the following design standards. These are our preliminary recommendations, and still working out the details with ODOT, and more details will be available in the ODOT Location and Design Manual once everything is finalized. But in general, our recommendations call for the amendment materials to be comprised of sand and compost. Again, this is because we didn't see much stormwater runoff benefit. Didn't see much difference between the sand and the expanded shale. So based on material cost, material availability, and really familiarity with the material as well, sand was the most effective choice. We also call for compost, again, for the nutrient and organic content benefits it provides to the existing soil and to the existing vegetation. And we are calling out a 6-inch incorporation depth. Now, like I mentioned before, we didn't see a whole lot of difference in stormwater runoff reduction between the 4-inch and the 6-inch amendment depth. But we felt that the 6-inch incorporation depth provided a higher level of homogeneity and overall more consistent mixing of the amendment materials into the existing soil. So ended up with a better mixture and an overall better product. So we are recommending the 6 inches. And again, not much cost difference between rototilling the soils to a depth of 4 inches versus 6 inches. So that was the most cost-effective solution. The construction procedure we're recommending is very similar to the one I laid out previously. First, we rip the soil in order to loosen everything up. We excavate the top couple inches off. And this is to, again, make room for the soil amendments that we're adding, because we don't want to change the existing grade or existing elevation of the existing condition. So we'll maintain that same elevation, that same profile. So we've got to remove a little bit of soil to make room for what we're adding. The amendments are placed and then incorporated with a rototiller, and we are specifying numerous passes in order to achieve that good mixture, homogeneity we're looking for. Then fine grading, and we're calling for limited compaction. This is a very specific type of compaction we're calling for. It's not the typical, hard, complete compaction that ODOT grading typically calls for, but we're calling for multiple passes with a smooth drum roller, and the intent is to compact the soils enough to provide adequate vehicle safety. We don't want to create a turnover risk in the event that a vehicle tire were to leave the roadway. We also want to provide a stable surface for emergency vehicles to cross the median if needed, as well as ODOT maintenance equipment, which is tractors and mowers. We want them to be able to operate as they currently do, no impacts to them. So we needed a stable surface, but we wanted to not fully compact it, so we still maintain some infiltration capability. We will apply a compost blanket along with seeding, water, and fertilizer in order to promote vegetation. And we're using standard ODOT highway seeding. So again, nothing special the contractor needs to get. And then protecting it with standard erosion control matting. Like I said, more details to come in the ODOT L&D. So like I said before, this is kind of just to reiterate, this is the construction procedure we're anticipating. And this would be for a, if we were doing a redevelopment kind of site, if we wanted to amend the existing soil along an existing roadway, which covered all that, just to reiterate with pictures. MS Consultants has also prepared some design standards to accompany the new BMP design. Again, these are preliminary recommendations we've made to ODOT, and additional final details will be available in the ODOT location and design manual. But the general guidance calls for a 2-foot minimum offset from the edge of paved shoulder. We don't want excavation or work being done right along the paved shoulder there, just to stay out of the road sub-base, anything like that. We're also calling for a 2-foot minimum from the toe of slope or the ditch bottom. Again, the BMP is designed to be installed along the sloped roadway and is designed to treat sheet flow from the roadway, not intended for concentrated flows within a ditch bottom. 4-foot minimum width for the amended area. That's consistent with the current vegetated filter strip that ODOT uses. 3-to-1 maximum slope, again, consistent with the vegetated filter strip. And that 3-to-1 slope max applies to both the amended area as well as any contributing area that's flowing to the amendment. So if the amended area is not started right at the top of the slope, but down the slope a ways, any contributing area that sheet flows to the amended strip cannot be greater than 3-to-1 slope. All runoff must sheet flow to the amended vegetated filter strip. No concentrated flows will be given credit, and they're not allowed due to their erosivity. So all sheet flow. And then must maintain a minimum 70% grass coverage. That includes the grass coverage of the amended soils area itself, as well as any contributing permeable area. So similar to the slope example, any area that's not amended but is upslope of the amended filter strip has to be maintained 70% grass coverage. Here's an example of the standard construction detail that is currently being developed by MS Consultants. and it shows the amended vegetated filter strip installed parallel with the roadway so it can capture sheet flow directly from the pavement. The amended filter strip will stop before the toe of slope, like I mentioned before. And we're also creating construction steps, you can see at the bottom there, that correspond to the pictures of the construction we reviewed a few slides ago, laying out the steps for construction, the ripping, the excavation, rototilling, and adding material, all that stuff. So there'll be a certain procedure, and this is to, what we found to be the most efficient way to install these, as well as to get the best results in terms of compaction and not running material over the amended areas after they've been constructed. So like I mentioned earlier, maintenance is minimal. It's going to consist of primarily the same routine mowing that ODOT currently performs along their roadways, especially with the typical grassed seed that we're applying here. It shouldn't really, once these things are installed, the idea is that the casual observer would never know that anything was different from a standard ODOT grassed side slope. But in general, the grass will be kept healthy, free of brush, woody vegetation, and then some routine inspection, which again is just keeping an eye out for signs of erosion or concentrated flows, rills, and gullies. And if any of those are observed, they should be repaired and stabilized in order to maintain the functionality and the maintain the functionality of the BMP. So the research team conducted a cost-benefit analysis for the amended filter strip BMP. And what we found was that the construction process and materials associated with constructing this amended soil BMP they overlap, and they share quite a lot with the materials and the procedures of a typical ODOT roadway project. So this results in a tremendous cost-sharing potential. The geometry of the amended vegetated filter strips is the same as a typical grass side slope or grass median. It's seeded with the typical ODOT grass. Erosion protection is necessary for really any disturbed area along a roadway project. So all that means is that these items essentially become somewhat negligible in terms of the cost of constructing the soil amendment BMP. There's no specialized equipment. It's all standard excavation and grading equipment that any contractor would probably have on site anyway. The materials are all very routine. They're easy to obtain and readily available in Ohio. So taking all this into account, the cost to treat one tributary acre of ODOT right-of-way using the amended vegetated filter strip BMP is about half the cost of traditional ODOT stormwater BMPs. And you can kind of see it compared to some of the more traditional BMPs like bioretention cells, detention basins, retention basins, etc. Additionally, these costs do not include right-of-way acquisition costs, which would only increase the cost efficiency of the BMP because the soil amendment BMP, due to its linear nature, very easy to install within the existing ODOT right-of-way versus a centralized treatment BMP like a detention basin or a bioretention cell requires additional right-of-way acquisition. The method for feeding these traditional centralized BMPs also poses an increased cost. Getting the water to one centralized location can be difficult at times. The amended filter strip BMP receiving sheet flow from the runoff makes it very conducive. No conveyance systems needed. Again, cost savings. So this image here shows an example of how the amended vegetated filter strip can be implemented on a typical redevelopment project. So this example looks at 10 acres of disturbed area, all within existing ODOT right-of-way. This results in a 20% treatment credit, and therefore for this example, the 2 acres of ODOT right-of-way is needed to be captured and treated to meet post-construction stormwater management requirements. So here is the implementation of the amended filter strip and how it's used to meet the ODOT stormwater management requirements. Based on the recommendations of the MS consultants, the amended vegetated filter strip area itself is given 100% credit. So any area that's amended is credited at 100%, while the tributary area within ODOT right-of-way, like the roadways, shoulders, that sheet flow to the amended filter strip are credited at 60%. However, the maximum width of pavement or upstream area that you are allowed to take credit for is limited to the width of the amended area itself. So for this example, we call for a 6.5-foot wide filter strip along the road. So while the contributing area for this center crowned roadway example is 24 feet, we only take credit for 6.5 feet because that is the width of the amended strip. So at the 60% credit for tributary area and 100% credit for amended area itself, we get a total stormwater credit of 2.06 acres, which meets our 2-acre requirement. I'll also note that this example assumes the crediting system that MS Consultants has recommended to ODOT. ODOT and the Ohio EPA are still negotiating the final crediting system. And so once that is finalized, it will be available in the ODOT location and design manual. So in summary, ODOT wants an alternative to underground storage and traditional stormwater volume BMPs that require extensive right-of-way acquisition. The amended vegetated filter strips are located within the existing grass area along uncurbed roadways within existing ODOT right-of-way. They are space efficient. They minimize right-of-way acquisition. The amended vegetated filter strips are good for offsite mitigation. They also increase the likelihood that runoff will be low. The amended soils improve the soil quality of the native soils, which along a typical ODOT corridor is going to be a lot of construction fill. Ohio soils are not all that conducive to begin with to infiltration. So improved soil quality is a benefit, and they're also cost efficient and easy to construct, especially as part of a large scale transportation project. And with that, I believe we have about 15 minutes to answer any questions. And thank you all for your time. Really appreciate it. I also want to thank again ODOT and their research group for facilitating this research, as well as all of our sub-consultants, USGS, Stone Environmental, and BUDS, Inc. So if there are any questions, I'm happy to answer them now, or my email as well as Greg's email are listed here for anyone that wants to send in a question after the presentation. Be happy to discuss with you. Thank you. Oh, one more thing. The final report, actually, I'm sorry. We're finalizing our report now, and it will be made available by ODOT once it's finalized. And the USGS report has also been finalized and is available from their website at the link below. And again, reach out to any of us if you need us to send you a copy of either report. Thank you.
Justin, you have all the questions. They've been assigned to you. We have quite a few.
All right, fantastic. I'm pulling those up right now. All right, there we are. Bear with me just for a moment while I pull these questions up. Yes, first question, to what depth was the subsoil ripped prior to adding the amendment? So we ripped to a depth of 12 inches. And again, that was just to loosen up the existing soil and make excavation and incorporation of the amendment materials a little easier. A good question. How deep was the compost blanket that was added to the top for benefit of seeding? We added a half inch of compost blanket on top during seeding in order to promote vegetation, germination of the seeds, and try to get that grass to come back as quickly as possible. Is there ODOT concerns with using compost blanket? Very good question. I would say I don't know if anyone noticed that or raised that concern in the field during construction. We are recommending a specific type of compost that's going to be a little different than ODOT's standard compost. We're looking for something with higher maturity, higher organic content, in order to really boost the soil quality of the existing soil and enhance vegetation as much as possible. So that is something we definitely will keep an eye on, but keep a nose on, because that's a very good question and had not been considered. So thank you. Did you specify a weed-free compost? Again, yes. We have a very specific compost specification that we're using, and it is, again, it'll be available in the ODOT location and design manual once everything is finalized. We do want a high organic content, but it's supposed to be very matured and broken down, so it should be free of weeds. Did you have any issues getting the 70% grass coverage at the amended sites? So funny enough, there were a handful of sites that did not reestablish as quickly as we wanted them to. We've associated this with, we actually did a quite extensive analysis on this topic in order to understand why that happened. We think it was a combination of environmental effects. After the seeding was occurred, we got a lot of rain that may have washed away some of the seeding. We also had a very dry drought that summer, which may have contributed to the establishment of grass. As a result, we actually amended our compost specification between what we installed in the field during testing and what our recommended alternative actually is. We amended the compost specification in order to better facilitate vegetation establishment and better assure that vegetation would establish quickly and efficiently and maintain robust standard vegetation. We also noticed that while it was a little spotty the first year of monitoring, we actually extended our post-construction monitoring a little longer, because the second year after the amendments were installed, they came back a little better. And I'm sure from out there today, they'd be back a little better still. So all those factors were analyzed, and we're kind of keeping an eye on that. But we do think that with our current compost spec and rototilling to 6-inch depth, that creates a very homogeneous and quality soil layer on top for seed germination. How do you take into account the underlying soil condition, i.e. heavy clay versus sand, etc.? So that's one of the reasons. In addition to capturing different rainfall parameters, we also spread our sites out across the state because we did want to capture a variety of soils. Soils are generally pretty consistent across the state in terms of ODOT right-of-ways. Again, it's a lot of construction backfill kind of material, so not a great deal of variation there. So the idea for this amendment was something that could be introduced across the state. So again, that's why we spread our monitoring sites out so we could get some variation. And we really didn't find that the geographical location had any big effect on the performance in terms of stormwater volume reduction. And then we took plenty of soil samples and that kind of stuff. So we had a variety of existing soils we were working with, and we think our amendment is very applicable to any soil found in the state. Will the width of the amended vegetated filter strip always be calculated based on the 20% redevelopment needed? So generally, I guess the designer is going to specify whatever width of amended vegetated filter strip is necessary to meet the stormwater volume requirement. So the example I showed, just for simplicity's sake, was a redevelopment project with a 20% treatment requirement. But this could also be used on a new construction project where your treatment percentage is a little higher, so you could make your amended width wider in order to get higher treatment, to meet a higher treatment requirement. It all just depends on the specific construction project. But so yeah, I guess to summarize that, we did size that 6.5 foot wide example just to meet the 20% requirement. It would have been wider if we needed it to. And then, does ODOT plan any ongoing maintenance assessment to see if mowing impacts the compaction over time? So yes, long story short, yes. ODOT is going to be monitoring these BMPs, both the performance, the vegetation establishment, maintenance, everything, just to see how they perform over time. That's a good question. And again, that's what we want, to provide some compaction, but we are very curious to see, I guess, what it does 5-10 years down the road. So it's something we will keep an eye on and monitor. Did you experience any on-site equipment damage during the tests? So actually, that is something we were anticipating, having our equipment adjacent to the roadway. There's always the risk of either a vehicle or snow plows, something interfering with it. That was one of the reasons we chose the widest medians we could find, really, because we wanted the equipment to be outside the clear zone for ODOT, just to minimize risk of vehicular or maintenance crews interfering with it. And the USGS maintained these gauges every month, went out there, performed maintenance. They mowed in the immediate vicinity around the gauges, just so the ODOT mowers wouldn't have to get too close to them. So to my knowledge, I don't think we saw any damage. I know there was one instance where someone went off the road close to one of our sites and left a big tire rut sort of right through our amended soil. But to my knowledge, no equipment was ever damaged. Greg, do you want to chime in there? Do you know of any damage we received?
Actually, Matt would be better to answer that question if he's on.
I am on, and you're correct, Justin. Nothing was broken or stolen.
Yes, I guess, yeah, stolen, that's a good clarification as well. Are there any terrain conditions that limit application of your management approach? So I guess, and feel free to send a clarifying question if I'm misinterpreting this, but I would say the terrain conditions, really the slope, is probably the biggest factor for that. 3-to-1 maximum side slopes for these to be installed on. In terms of longitudinal slope, again, we're working out the final details, and they'll be in the location and design manual. But because we're not amending within the ditch line itself, longitudinal slope shouldn't have that big of an impact. Essentially, if you can build an ODOT roadway at a certain slope, you're going to be able to build an amended vegetated filter strip parallel with that roadway at that slope, and it should be fully functional. But other than that, no terrain, no other really terrain conditions, no. ODOT right-of-ways are typically very open grassed areas, so nothing too complicated there, nothing that we saw. All right, so that's all the questions I see. We still have another maybe 5 minutes if there are any more. Otherwise, I appreciate everyone's time, and feel free to reach out to either myself or USGS with any additional questions.